For this problem, we consider a rectangular profile for an element or material under shear and make a comparison with the average shear stress in this single shear configuration to the maximum bending stress that we would have for a beam under a similar loading condition as we change the length L. And to review what single shear looks like, we can put this image back up that we have where there's a pin that is being pulled apart from two plates that are very close to each other. The region under shear is between these plates, or in this region right here where I'm pointing the mouse. We can model this type of system as a beam as well. Now, this may be a little bit of a stretch, but imagine that this wall is this portion right here that's being constrained by this plate acting on this portion of the pin. And then this is going downward with P being this force, and it's pulling it in this direction like you see here. We've chosen this model for beam bending as similar instead of saying doing a wall-wall type configuration because it is a determinate system that will only be describable, or we only need to describe through equilibrium. When we have the beam, we think of what's happening on the left side with a reaction bending moment from the wall and a reaction force from the wall. We could have drawn these in either directions. We don't have to follow a convention when you're looking at the external loads on the beam. And this beam has on the right at point P or above it or through it a force of P. The cross section is given as follows, where we have a width B and we have a height H. When we draw the shear force and bending moment diagrams, we get the following, and we've done this type of problem. What's this? Meaning the cantilevered beam with a single load acting transversely through it in the past, and the profiles look like we have here. Now, the bending moment scales with length, which means the internal shear force will dominate bending moment for small lengths. So if you have a very short length, the P, or a very long length, the P for the shear force doesn't change, doesn't vary. But if you have a very small length for a beam, what you see is that the L gets smaller and smaller and smaller. And when that happens, the bending moment that you'll be calculating is also going to have a smaller magnitude. So at some length, we get to some whatever length that will make the bending moment be a higher contributor to the stress that would cause failure than this shear force that we have, and we can think of an average shear stress associated with it that would also potentially cause failure. And later in the course, we'll make it more clear why there's significance between shear stress and half of an axial stress. When we cover more circle, it will be particularly clear. But for now, let's just say that that's the comparison that we're interested in making, that the average shear stress be half the maximum bending stress. And when this maximum bending stress is exceeding this quantity, then the bending stress would dominate. And when it's less, when the length is low and this maximum bending stress is lower, then the average shear stress will dominate. So the average shear stress in the single shear configuration is simply the force P divided by the cross-sectional area. And the maximum bending moment, as we said previously, is going to be here at the wall where we have a magnitude of PL. The equation for the bending stress is going to be minus my over I. And if we look at the average shear stress with the dimensions that we have, we can say it's P over BH, BH being the area. The maximum bending stress, when we look at this problem, is going to be the bending moment, PL, times half the thickness. Okay, so that'd be H over 2, because that would be the distance between the neutral axis and one of the outer surfaces. So you have a neutral axis across, right? And then we're looking at h over 2 or h over 2. And for now, we are saying that a combination that we pick, so it could be y equals minus h over 2, and this, or actually it could be h over 2, and this minus the p minus the PL will give us the PL h over 2. And that means that this top portion right here near the wall, that is under tension. The I, the second moment of area, is going to be the BH cubed over 12. And that's what you see in the denominator. So for what L do we have the average shear stress equal to half of the maximum bending stress? And we can write out that the shear stress is equal to this maximum bending stress that we've calculated. And there's only an L on one side, so we can solve for that L and determine that the height, or sorry, the length, okay, L, is going to be equal to h over 3. Okay, so that we get these h's, they knock out, at least, well, one of them knocks out the other one. P's cancel, the b's cancel. And so what this means is that if the height of the, or sorry, if the length of the beam, okay, is greater than h over 3, that's not very much. But if it's greater than h over 3, the bending stress is going to dominate. Okay, so you can imagine now if the gap here, that's what we're defining as the length, if that gap is greater than h over 3, for this particular model, we're going to say that the bending stress dominates. And if the gap between these, or the length between these, is less than h over 3, the thickness, okay, that will, or the thickness divided by 3, then we'll say that the shear stress under single shear is going to be what dominates. I hope you found this video useful. Thank you.